So let's review just for a minute. So we have alpha decay, and that emits 2 protons and 2 neutrons. And that is written as a 4 up here because the weight, the atomic weight, is going to be the protons plus the neutrons, so 2 plus 2 is 4. And then down on the bottom is going to be the 2 for the 2 protons. And we just have a capital E for a generic element. But if we look on the periodic table and we look up the atomic number 2, we see that helium has the mass of 4. So that's really what it's doing, is it's emitting a helium. So that's 1. 2 is beta decay, and beta decay, the neutron emits an electron. So that's a 1 charge. So the neutron turns into a proton because by definition neutrons have to have a neutral charge. If it is let go of a negative charge, that means it's become positive, and by definition a proton is what has a positive charge. So that is written 0 up here because no mass or no weight was changed because we're just talking about a charge, and -1 goes down here because it's emitting a negative charge, an electron, and we use the lowercase e because we're talking about a charge. Now number 3, positron emission, is just that, because what's a positron? A positron is the positive charge on a proton. So a proton emits its +1 charge, which turns it into a neutron. Because by definition, a proton has to have that positron, that +1 charge, in order for it to be a proton. If it doesn't have a +1 charge, if it has a 0 charge, then by definition it's a neutron. And that looks almost the same as the beta, because you have 0 up here because we're dealing with charges, so we're not losing or gaining any mass, but we're losing a positive charge. So this is just going to be a +1, not a -1. And we use the lowercase e because we're talking about charges. Now the final one is that crazy funky looking V, and it's called gamma decay. And there is no change. So it would be 0, 0, E. But we don't really write it like that. We just write the gamma decay. It gives off a gamma ray. So let's get to some of these practice problems. So the first one is if we have a beryllium-7 isotope, and the atomic number for beryllium is 4, so we're going to put 4 down there. And somehow it changes to a lithium-7 isotope, and the atomic number for lithium is 3. What has to change here? What has to be added to the lithium here in order for it to start out as the beryllium-7? So pretty much you want to just complete the sentence or complete the equation. What would make this equation true? If beryllium-7 turns into lithium-7, what made that happen? So let's look at the differences between the two. We have 7 up here, and we have 7 up here, so there's no change. So since there's 0 change in the mass, we're going to write a 0 up there. But down here we had 4 protons and now we only have 3 protons. So somewhere around here, a proton flew off, or a proton changed its shape. Really what happens is that the proton doesn't go anywhere. The proton's positive charge goes somewhere, which turns the proton into a neutron. So the proton gets turned into a neutron. So that would be a positive 1 down here, and we're going to put a lowercase e because we're talking about charges. We're not talking about actual protons or neutrons or electrons moving in and out of the atom. We're just talking about the charge leaving. So the 0/1 lowercase e, that's going to be a positron emission. And see, the proton turns into the neutron because the proton emits its positive charge right here. Now what about another one? What about uranium 238? Uranium 238 is an isotope, and you should know by now that that it can be written like this. That's fine. But when we write it to do formulas with it, you know, we turn it into a little Scrabble piece, and we have the U here in the middle, but we put the 238, the weight, up in the upper left-hand corner. And if we go over to our periodic table, uranium is, where is uranium? Look for a U. Oh, okay, way down here on the bottom row here in the transition elements, uranium is right here, and you can see its atomic number is 92. So that's what we're going to write on the bottom. Let's go back to our formula. 92 is what is how many protons it has. That's its atomic number. So we're going to write that on the bottom. So what if we have something like this? Uranium 238 turns into thorium, and that's a TH, that's its symbol. Thorium 234 isotope. And if we look on this periodic table again, where's thorium? A TH. Well, that would be right down here, 2 elements below uranium. And look, its atomic number is 90. So if we go back to our worksheet, we'll put 90 for the atomic number down here for thorium. Now, what would have had to happen in order for uranium 238 to change into thorium 234? Well, let's look at the differences. What's the difference on the left side of the yield arrow versus the right side of the yield arrow? First, we have the weight is 238 over here. Thorium's weight is 234 in this isotope, so we lost 4. And then down on the bottom, uranium's atomic number is 92. It has 92 protons. Thorium has 90 protons, so we lost 2 protons. So what's going to happen? We're going to have a 4 up here because we lost 4. And we're going to have a 2 down here because we lost a 2. And we can do this as just an E for a generic element. But if you look up on the periodic table, helium right here is atomic number 2 and a mass of 4. So we're going to go back to our formula, and instead of that E, we're going to just go ahead and admit, yeah, it's a helium atom. Now what is this one called? This would be alpha decay, because it gave away a helium. It gave a helium away. Now let's do another one. We have an isotope of iodine 131, and iodine is 53 on the periodic table, its atomic number. And iodine 131 changed into xenon 131, and xenon's atomic number is 54. So what had to have happened for iodine 131 to change into xenon 131? Well, let's look and see what the differences are. Now 131 and 131 is the same. It did not change at all. It stayed the same weight. So we know we're not going to be getting rid of a proton or a neutron, an entire proton or an entire neutron. We're probably going to be dealing with a charge. So since the weight stays the same, this is going to be 0 because there's no gain and no loss. Now down on the atomic numbers, 53, and it changed to 54. So we gained 1 proton. And that's why it changed the element to xenon, because by definition, if you have 53 protons, it's iodine. If you don't, if it's a different atomic number, it's a different element. Only iodine is only 53. So we gained a proton right here, which means in order for iodine to have changed into xenon, we had to have gained 1 proton. That's going to be minus 1 charge. So if we're dealing with charges, we just write a lowercase e right there. And this is going to be beta decay. Beta decay. Because see, this is this exact same thing. Now, why would I put a -1 here when we went from 53 to 54? Well, it's just because of math. If you have 53 equals 54 plus what, you're going to have this question mark is going to have to be a -1. So 53 equals 54 plus -1. Now here's a different problem. We have iodine 123 and its atomic number is 53, and we have the yield arrow and the sign for a gamma ray being given off. So if a gamma ray is given off, what happens to this original isotope here? Well, first of all, we need to fill in the blanks. If a gamma ray is given off, then that means automatically that this original isotope of iodine 123 gets an asterisk next to it, because that means it was excited, and it was excited enough to give off a gamma ray. So it has to be excited in order to give off a gamma ray. So we put the asterisk there, and then what happens after the gamma ray is given off? Nothing. It's just it just doesn't, the iodine 123 just isn't excited anymore. It doesn't have any change whatsoever, except this one after the gamma ray is shot off does not have an asterisk, so that's not excited. So it's not excited anymore. So the answer to this would just be plain old iodine 123 isotope. And it's worth noting that this gamma ray that is shot off is also called a photon. Well, it's a type of photon. Not all photons are gamma rays, but all gamma rays are photons. So a couple more problems. We're going to do the 144 CE, and that has an atomic number of 58. And this is how the problem is set up in your practice workbook. So let's look and see what the difference is before the yield sign and compare it to after the yield sign. So before the yield sign, this is 144. After the yield sign, this is 144. So we know the top number in this answer is going to have to be 0. Now on the bottom for the atomic numbers, this was 58, but this one was 59. So proline will have to lose a proton in order to become 58 back here. So we're going to put a and we're not really losing a proton, we're losing a positron. So I should actually write that correctly. Lose a positron. And what's a positron? A positron is the positive charge on a proton. So without its positron, the proton is not positively charged and it turns into a neutron. So going back to the answer up here, so this would be a -1 because we're losing the positive charge. And since we're dealing with charges and we're not dealing with the elements so much, the protons and neutrons and electrons, we're dealing with the charges of them. We're not dealing with an entire proton. We're going to put a lowercase e. And so this should look familiar to you because this would be beta decay. Now here's one that's set up a little bit differently. See, it already tells you that we're dealing with alpha decay because it's the helium-4 that we're losing. So we know that, but what is this element going to be right here when this helium atom is taken away from this right over here? So let's compare the differences just like we did with the other things. We have 212 over here and 4 is given off, so we only need 208 left to make that 212. Down here, this 84 is the atomic number. 2 is given off, so we only need 82, only 82 protons in this part of the equation. So how would we figure out what element this is if we have an isotope weighing 208 units and 82 protons? Well, we'd look at our periodic table. We'd look at our periodic table for the 82 protons, which will be the same as the atomic number. So the 82 protons is right here. See the 82? And that's Pb, lead. So let's go back to our chart and we will write in Pb, and that is going to be our answer. And this 4,2 helium, this is an example of what? Do you remember? Alpha decay. Now here's another one, and it's just set up differently. This says give the alpha decay of Ca231, so that's an isotope. And alpha decay, do you remember what alpha decay is? Alpha decay is when we give off a helium atom. So we're going to start with, let's get a different color. We're going to start with Pa, isotope Pa231. And how do we find out what the number on the bottom is? We look at the periodic table. Oh yeah, it's 91 right here on the very bottom. Pa is atomic number 91. So now let's go back up to our sheet. So we'll put 91 there for Pa. And then a yield arrow. and we'll put the alpha decay there, plus, now plus what? What do we need to put with the alpha decay to get the Pa231? Well, let's look at the differences here. If we look at the 231 from the Pa, and we already have 4 accounted for from the alpha decay, so we only need 227. And then we look at the bottom here, we have 91 protons here, that's the atomic number, and we have 2 already accounted for in this alpha decay, giving off this helium atom, so we only need 89. So how do we find out what element that is? We go to the periodic table and we look for 89. So 89 is right here on the very bottom left of the 2 separate rows, and that's AC. So let's go back to our board, and that's isotope Ac227. Now here's another one, and it's almost the exact same thing, but the difference is that this is asking for the gamma decay of Pa231. So we already know how to write Pa231 in isotope notation. And do you remember from the periodic table what the atomic number was? Let's go and check and make sure. There, Pa is 91. So let's go back to our chart and we'll write 91 on the bottom and a yield arrow. And remember, the gamma decay doesn't have like a fancy Scrabble tile to it. It's just that funky V, because that funky V indicates it shot out a gamma ray, which is also a photon. So you can say photon or you can say gamma ray. Not all photons are gamma rays, but all gamma rays are photons. So a gamma ray is a type of photon. So we have the gamma ray that shot out plus what? What would result after this Pa231 shooting out a gamma ray? It's the exact same thing, because the gamma ray, a gamma ray has 0 weight to it and 0 charge to it. It's just that it excited the Pa, so we put a star by the Pa to show that it's excited. It excited the Pa so much that it shot out a gamma ray. So we didn't lose anything. We still have 231 as the weight, and we still have 91 as the number of protons. So that makes it still Pa231. And I hope that helps. That should about wrap it up. If you have any questions or comments, please leave them in the comments. Don't forget to like and subscribe. Thanks.